Okay, okay.
It's not very dense.
How many of you are depending on the first question? How many of you are depending on the second question? Man, it's always amazing to me how it's evenly split. How many of you are Democrats? How many of you are Republicans?
Actually good.
There's a lot of apolitical people.
You assume that there's only bad or apolitical.
Yeah. Don't give me a lecture. Okay, so we're going to get started.
You don't. Do you want to hear my communist anarchy?
We're going to get started with today's stuff. This is good stuff today. We're going to take what we did last time a little bit further. My turn. Kate, put that phone away. Don't make me come and get you. My turn to talk. You had your chance, and you all just sat there quietly for some stupid reason. So you snooze, you lose. All right. So I'm going to start with just a clarifying point, and then we're going to get into something that's interesting. And it's actually one of my favorite little discussions of the semester because I think it's really concrete. Except I tried to explain this to Gabriel about 2 weeks ago and he was utterly confused. So I don't think it's as concrete as I think it is. But I'll let you be the judge of that when the time comes. So far, we have two good derivatives that we've been working with, and I just want to kind of remind you of them and highlight their differences because we're going to make extensive use of these derivatives in the course. So first of all, we have this thing that we call the covariant derivative. And the covariant derivative, as you are all familiar, is expressed by del mu, and then as it acts on a vector, for example, of course you can let it act on any tensor, but when it acts on a vector, the interpretation of what we're doing, and there's a formula for what this looks like, the interpretation for what this is doing is it's taking some interval in space-time coordinates and you're considering the difference between the vector evaluated at the shifted position minus the value of the vector at the original position and then dividing that difference by delta x mu, okay? And the reason I'm writing this sort of more formal definition up there is to remind you that the notion of parallel transport plays an important role in this derivative, in giving this derivative an interpretation. And we kind of finished our last lecture by talking a little bit about what parallel transport means and is and looks like. And we gave you a formal definition for it. Okay, there's another derivative that is useful, and that is the directional covariant derivative. And the notation for this is going to look a little bit different. It's going to be big D of a vector, for example, d lambda. And just to give this a formal interpretation, what is happening in this case is we're taking a vector and we're parallel transporting it, but we're parallel transporting it not by just some coordinate shift, but by a shift along some path that is parametrized by some quantity lambda. Okay? So what do I mean here? So the covariant derivative itself is a derivative where you set up a coordinate system in the space, you know, and if you've got 4 dimensions with time like that, and then what this derivative computes for you is how the vector changes as you just take a shift along any of these coordinate axes. So you pick a value of mu, say you pick 0, then you're calculating the change in this vector as you shift by epsilon along the t-axis, or by some delta t, okay? And then similarly, you can use this to calculate the change as you move in x, y, or z. And of course, this is done in a very special way to take into account the fact that you can have both the components of the vector change, but also the basis that you're using for everything change, and that's part of the formal expression for this. Now the directional covariant derivative is a slightly different thing, because what it says is, forget about the space for a moment, and let's just take a curve, okay? And so I've got my space, and I've got some curve through the space, and I have some vector field, so there's values of vectors all around the space, and if I just pick some point on the curve lambda, then the vector field is going to have a value there. And now all I'm asking is, if I shift along the curve by a small amount delta lambda, how does the vector field change as I shift from this point to this point? Now, of course, in order to describe this, what we normally do is we coordinatize the space, and then we describe this curve in terms of some x mu lambda, okay? And so that's why this expression more formally can be thought of as the vector field depending on x mu, which itself depends on lambda. The only point I'm trying to make is that this is the derivative along a very specific curve, and this is just the derivative as you move along each of the coordinate axes for whatever coordinates you've chosen to set up. Okay? Now, clearly, because this definition can go by way of using coordinates, we can rewrite this in another way, and that is in the form dx mu d lambda times the covariant derivative of v nu, okay? Because all this is saying is, all right, if I want to know how v varies with lambda, the first thing I can do is figure out how v varies with the coordinates, and then figure out how the coordinates vary with lambda, and then just smash those two things together, okay? So this is worth writing down, because we will use it a little bit later, as your definition of the directional covariant derivative in terms of the regular covariant derivative and then a derivative of the coordinates with respect to the parameter of the path you're dealing with. Okay? All right. Any questions about that before we go on? Okay. So, we're now going to talk about a subject which, off the cuff, seems like a little superfluous, but it actually plays a very central role in general relativity. And this is the subject of geodesics. So let me start by reminding you of sort of the bigger role played by geodesics in general relativity. So at the very beginning of the semester, I sort of laid out an analogy for how general relativity compares to E&M. E&M is a theory with which you're pretty familiar. So we know that in E&M, we have half of the theory is given by Maxwell's equations. And my first victim, Ryan. Where are you, Ryan?
Oh, he just went to the bathroom.
Just went to the bathroom. Awesome. Okay, didn't want to get the back. Chase. Chase, what do Maxwell's equations tell us? In words, not in. No, don't recite the equations.
Sure. They describe like electromagnetic fields at constant space.
Okay, and in particular, what about those fields?
Divergence and curl.
And that's the mathematical aspect of them, but like, what does it relate the fields to? So what's on the right-hand side of many of Maxwell's equations? Or of a couple of Maxwell's equations?
Charge.
Sources. So Maxwell's equations tell us how sources, charges, and currents create fields. Okay, that's half of E&M. The second half is to say, okay, I create electric and magnetic fields. Now I want to describe what a charged particle does when I stick it in that electromagnetic configuration. And just to make sure I get enough victims today. Alex. Oh, you're here. Where are you? There, Alex. What tools do we use to describe how things behave when we put them into electric and magnetic fields?
Test particles, or test.
That's what we're using, but what is the mathematical machinery?
Vector calculus.
It is vector calculus, but we have a name for it in physics.
Are you talking about like the Lorentz force law?
So we have a Lorentz force law, which tells us the force that gets created, and then we use Newton's second law to actually determine the motion of the particle. Okay, because once you have a force, you have to tell me, okay, well, how does that affect the motion? And that's what F equals ma tells us. So the second half of this story is the Lorentz force law plus Newton's second law. Okay? So that's sort of the story of electromagnetism in a nutshell. All right? You engage invariance included. Now in general relativity, we have a very analogous split. Einstein's equations, which we're going to develop over the course of the next couple of weeks, we've been developing, but we're really going to put them in their final form. Einstein's equations in GR are going to play an analogous role to Maxwell's equations in electromagnetism. That is, they tell us how sources create curvature, or how sources influence the geometry. And of course, by sources here, I mean any form of energy or momentum, and mass is included in that because mass is part of energy. The big question, though, is what occupies this spot? So we have like a star creates a curved geometry, and we want to know, what if I put a little satellite near the star in orbit? How do I, what tool do I use to determine the motion of a satellite in the presence of the geometry created by a star? Any guess?
Geodesic.
You use the geodesic equation. So, in words, the result is simply that if you're only thinking about the force of gravity, if that's the only force you're worried about, so forget about electricity, magnetism, strong nuclear forces, if you're only thinking about gravity, then the gravitational force on an object forces that object to move along a geodesic trajectory. And I'm going to define what geodesics are in a minute. Okay? But this is telling you both how the particular force of gravity and how it influences motion. You move along a geodesic path. Okay? So we're going to fill in the story of geodesics today. Now there are two ways to define a geodesic, and each have their strengths and weaknesses. So I'm going to call a geodesic path, and we can, if you know, it's going to be literally like a curve, because it's a path of an object. You can just think of like a point if you want, a point particle. And I mean, to good approximation, everything we think of in general relativity that's following a geodesic is a point particle, because like a satellite compared to the sun is effectively a point. So if we want to define, and I'll call a geodesic by this little subscript, geo, just to separate it from an arbitrary path. There are two ways to define these. The first is that they are curves which extremize the distance between points. Okay. This is a definition with which, if you've ever heard the word geodesic, you're probably somewhat familiar. Okay. But there's this idea that if I pick 2 points and I ask what is the curve between them which extremizes the distance, that's a definition of a geodesic. Now many of you have probably encountered this notion, if at all, in the context of flat space, not space-time. So in that context, the statement would be, what is the curve which minimizes the distance between 2 points? And you all know the answer to that. It's a straight line in the simplest scenario. It's certainly not going to be a straight line in more arbitrary scenarios. Okay? But this is the more formal version of that. I have to use the word extremize for reasons which I'll talk about in the course of today's discussion. Okay? It's not always a minimization. Okay, so the second definition is one which is actually going to allow us to do something a little more formal in terms of the math. And the second definition is these are curves which parallel transport their own tangent vectors. Okay? Now, that second definition is the one I'm actually going to beat on the most, but it's actually, as abstract as it sounds compared to this one, it's actually going to give us a really, really nice visual interpretation of what is and isn't a geodesic and how it depends on the particular space that you're talking about. And then we'll come back a little bit later on and connect the ideas we develop in terms of this definition to the ideas developed in terms of this definition. So I'm just going to proceed with a couple of examples. So let's first of all consider a very simple space. That's just a real two-dimensional spatial plane. We won't put time in the story right now. Put it in a little bit later. And one thing that we know is if I pick 2 points in this space, say point A and point B, then I know the geodesic path between A and B. It is? It's a straight line. This is a very simple scenario. Okay, nothing weird here. But now let me do the following. Let me say at point A, what is the tangent vector to the path? So it's a vector which points parallel to the path at the point A. Okay? So if I came in with the green marker, the tangent vector would look something like that. Okay? Now, if I scoot down the path a little bit to another point and draw the tangent vector, what I discover is that as I move along the path, I end up with a sequence of vectors, each of whose tail is meeting the head of the other one. Exactly like a choo-choo train. Okay? And this is an illustration of the fact that because this is a geodesic path, the tangent vectors actually remain parallel to each other. Now that is such a trivial example that it almost obscures what I'm actually saying. So let me draw you a non-trivial, or actually a non-geodesic example, so you can understand the distinction. So in the same space, so I'm still in R2, I'm going to pick a different path from A to B. Okay? I'm going to pick a non-geodesic path between A and B. So anything that's not a straight line. So I'll just do something simple like maybe an arc, like that. Okay? And now what I can do is again construct the sequence of tangent vectors. So starting at A, and then as I move along the path, I keep the vectors tangent to the path. Again, creating this sequence of vectors that are connected end to end, just like a bunch of people dancing the conga. Okay? Now here's the key. These vectors are all parallel to each other. These vectors are not. Okay? In fact, if you take the vector that you start with and you parallel transport it to the point B, that vector would actually point like this, which is definitely not parallel to the final vector that we would get of tangents along the path. Yes?
So if they were parallel, then that would be the geodesic. Like that's the definition. That's what we're trying to say, right?
So what I'm saying is that this is an example of a geodesic and it satisfies this property. This is an example of a non-geodesic and you can see that it does not satisfy this property. That's all I'm trying to illustrate here. Okay? Go ahead.
Is it not a geodesic because it doesn't satisfy that property, or is it not a geodesic for a different reason?
It's not a geodesic. Well, you're getting meta on my ass. I mean, like, if I define something and then you go, is it not that thing because it doesn't satisfy the definition? Like, that's not specific to the physics context. I think this is what you're doing is you're saying, well, let me say it this way. I am relying first and foremost on your familiarity with this to be able to say this is a geodesic and this is not. And I'm using that as a starting point for you to get comfortable with this, which is more abstract, but more powerful. Okay? But yes, these are the conditions defining geodesics. This satisfies neither of them, therefore it's not a geodesic.
Does it only have to satisfy one to be a geodesic?
Satisfying one will be equivalent to satisfying the other, and we'll show that. Okay? So they're not independent conditions.
So in this case, we minimize the path, but if we maximize the path between A and B, you get something infinite.
So maximizing the path, whether you minimize or maximize the path, is not a free choice. It actually is dictated by the space you're working in.
Okay.
So when you're in real space, in Euclidean signature spaces, you're minimizing the paths. And we'll talk about the cases where you maximize the paths in a few minutes.
On like the surface of a sphere, can't you do both?
So on the surface, and I'll come to an example like that, but on the surface of a sphere, well, no, you're thinking of something a little bit different on the surface of a sphere. Okay, the surface. So the surface of the sphere, I know what you're thinking of, but it's not directly addressing this. On the surface of the sphere, if I pick 2 points, then there's a path which maybe goes like that. That's the shortest path between the 2 points. But then there's another path that goes like that between the 2 points. This is not the maximum length path. Right, you could draw a path that wanders infinitely. So the maximum length path in a real space doesn't really make much sense. It's not really well defined. Okay, but I agree with you, there's sort of an ambiguity, and it's particularly the case in a circle, where you do have a maximum path and a minimum path between 2 points. But for a sphere, no. But that's not going to be too much of a concern. Okay, so now to really drive the point home, instead of thinking of this story in one space with 2 different paths, I'm actually going to now do the story in 2 different spaces along what is ostensibly the same path. Okay, let's do this. All right, so and I'm going to actually do this a slightly different way. So in R2, I'm going to start with an example which is essentially this. So in R2, I'm going to consider the path between A and B, which is just this sort of arc of a circle. Okay? And then over here, I'll draw that in a minute. Okay, now what I'm going to do in this case is, it's the same argument I made here, but I'm going to draw it a little bit differently. In this case, what I'm going to do is I'm going to take the tangent vector in A, and I'm actually going to parallel transport it along the path. Okay? So remember, as we parallel transport, at each point we keep the vector as parallel as we can to the preceding vector. And so we end up with this really weird looking picture, which in some ways kind of looks like this object with many legs, but makes me think more of Pinhead from the Hellraiser movies. You're not going to get me to say it. It's inappropriate. Okay? So, again, by parallel transporting this initial tangent vector, we get to the same conclusion, and that is, this is not a geodesic. Because if I start with a tangent vector and parallel transport it, it no longer remains tangent. Alternatively, if I consider all the tangent vectors, they're not parallel to each other. These are both demonstrating that this is not a geodesic. But now I'm going to do one thing which changes the story. Okay? So this is a geodesic. This is not a geodesic. This is not a geodesic. But now I'm going to take this exact same curve and make it a geodesic. So if instead of being in R2, which is the two-dimensional plane, if I'm actually on the surface of a circle, well, first of all, the shortest distance between A and B on the surface of the circle is exactly this path. So by the first definition, this should be a geodesic, and in fact it is. Okay? But let's see how it satisfies the second criteria. First of all, let's start with a tangent vector at A. Okay? If I take that tangent vector and I want to parallel transport it, I want to keep it as parallel to A, or to the vector here, as I possibly can. But when I get to the next point on the path, notice I cannot draw a vector that points like that. The vectors have to live in the tangent space. They're forced to live in tangent space. So I am forced to have the vector at the next point look like that. And then so on all the way down the path. Okay? Now be careful, because this picture looks a lot like this picture. If you just focus on the path and the vectors I'm drawing. But they are two very different situations. Here, everything off of the curve is part of the space. The white here is part of the space. So vectors could poke out there if they wanted to. Here, though, the white stuff doesn't exist. The only space is the surface of the circle. Okay? But you'll notice what's happening. I am parallel transporting the vectors, but they are themselves tangent to the path, which satisfies criterion 2 for a geodesic. Okay? Does that make sense? Yes, Alex.
Is that equivalent to just a straight normal line in one dimension?
Here? Well, let me say this. So if I did not tell you that that this was constrained to the surface of the circle, and I said, what's the shortest path between A and B? Most people would draw this line. Of course, the point is that line is not a path on the surface of the circle. That line is not allowed. It's going into a space which does not exist. So yes, there is a sense in which this is your best approximation to a straight line, given that you're forced to live on a circle. But I'm not going to call it a straight line. I'm just going to call it a geodesic. That's the name for it. Straight line implies too much, and I don't want to stick with that. Okay? Questions? All right. Okay, so if this gives us sort of a sense of what geodesics are, now we're going to use some of our results to formalize the math describing geodesics. So what we want to do is we want to use the two notions of parallel transport and tangent vectors to sort of write down a mathematical condition that reflects this. Okay? So you might remember that if we have a path parametrized by lambda, then the components of the tangent vector are given by dx mu d lambda. Okay, that was part of the lecture where we were actually constructing tangent space as the tangents of all of the different curves that pass through a point. And that's where we discovered the basis of vectors and the basis of dual vectors and so forth. And then what I'm going to say is the following. If a curve x mu lambda is a geodesic, that is, it's actually x geo, then the tangent vector should be covariantly constant along the path. Remember, parallel transport is keeping a vector constant. That's the idea. You're not changing the vector. But what this says is that when you do the parallel transport, or if you just actually consider the tangent vector to a path, that tangent vector is being parallel transported. And in the process, it's not changing as you move along the path. Okay? So if I actually write down this condition mathematically, what we're insisting is that the directional covariant derivative of the tangent vector, so that's the tangent vector, that's the directional covariant derivative along the path, parameterized by lambda, this should be what? Should be 0. Yes. Hello. Don't worry. No. This should be 0. I'll wait till something hard pops up. Okay, but let's go back and remind ourselves what the directional covariant derivative looks like. D by d lambda is dx mu d lambda, and I'm going to put a nu here, times the covariant derivative. Okay, so as per the first thing I talked about, that's a way to blow up what the directional covariant derivative looks like. And then this thing right here, it's just a vector. You can kind of squint your eyes and see it has a vector index. Okay? So this is just what we're taking the derivative of. Now, we of course know how to take the covariant derivative del nu of a vector, and so we can blow up the right-hand side of this a little bit. And I'm going to use alpha, good. Okay, so this is an expression that you should all be very comfortable with after your homework. We're just blowing up how del nu acts on a vector, in this case dx mu d lambda. Oh, whoops. I will do it this way. Nope, I can't do it that way. I can't do it because the indices don't work out. So this is going to be dx mu d lambda plus gamma mu nu alpha dx alpha d lambda. Okay. And now we can just do a little bit of massaging of this to find an expression of the following form. This is equivalent to d2 x mu d lambda squared plus gamma mu nu alpha dx nu d lambda dx alpha d lambda. Okay. The d2 x mu d lambda squared is just recollapsing this term. Okay. And this is what we call the geodesic equation. Write that down, we're going to do a lot with it. Now, before I actually start kind of showing you some examples to make this explicit, let's just think for a moment about how we would use this. Okay, Meadow? What order is this differential equation?
Second order?
Second order. Ryan, did you come back? Where is it, Ryan? Ryan, how many boundary conditions do we need to supply in order to provide a unique solution of this differential equation? Two. There are two different ways that we, yeah, that's right. There are two different ways that we tend to use this. One way that we use it is we specify an initial position. Say, where is your coordinate position at some initial parameter of the curve lambda naught? And then we can secondly specify your initial velocity. Okay, so that is, we're starting you out at some point with some initial direction. And then with this initial data, you solve this second order differential equation, and that will basically give you the path that you're going to move on based on that initial data. So the solution would be some path, you know, which depending on the space might look weird, and that would be your geodesic path. This is the way we use this equation in general relativity. Because in physics, what we tend to do is say, okay, I've got these forces set up, I'm going to put the ball here at rest, and then let go. What does it do? That's equivalent to saying I'm going to give its position initially, its initial velocity, and then solve whatever the equations of motion are to figure out what's going to happen. That's not the only way you can work with this differential equation. Alternatively, we can specify an initial position and a final position. All we need is two pieces of information. Okay. But if we specify an initial position and a final position, then when we solve the equation, we're finding the path which extremizes the distance between those 2 points. That's the way you use the geodesic equation in the more familiar context of, I pick 2 points, what's the shortest path between them? So the data you're giving to the second order differential equation is the initial and final locations. Of course, you could change all this up. You could give the initial and final velocities and use that as the data, or you could use the final position and the final velocity as the data. It doesn't matter. In practical applications, we either use the initial position and velocity or an initial and final position. Okay? I'm spelling this out to you because in your next homework assignment, you're going to be solving this differential equation. Yes?
So if you gave the initial and final velocities, would you get a set of paths?
That's a good point. You would have a set of paths. Is that well posed? Yeah, that might not be well posed. Yeah, I might have to actually, yeah, that might not be well posed. I mean, you would obviously be able to translate the entire system, but it's still, even up to that translation of the overall path, it still might not be well posed. But we're never going to use those conditions anyway, so I'm not going to worry too much about it. Okay, so before I take this and look at some non-trivial examples, let's actually look at a trivial example of how this equation works. If you want to talk about geodesics, what space makes everything really trivial? R2, exactly. So in R2, we don't even have to do any work. We know the answer, but let's actually see how the equation works in R2. Well, actually, we'll do R3. I know. So if we choose to work in R3 in the XYZ coordinates, for that particular choice, Jonathan is going to remind me of what the Christoffel connection components look like.
0.
Yes, they're all 0. Remember, you build these things by taking derivatives of the metric, but the metric for this space is just 1, 1, 1. Notice if I change the coordinates, if I use spherical polar, then suddenly some of these are non-zero. So that's why I have to give you not just the space, but the coordinates that I'm using. okay? But for this particular space, all of the gammas are 0, which means that the geodesic equation simplifies to d2 x mu d lambda squared is 0, because all of these second terms disappear. But that's actually a differential equation that you can solve. Okay. Look, it says the second derivative of this function, and remember this is a function of lambda. The second derivative of the function vanishes. Okay. It means the function is a straight line. So my path is just a linear path. Lambda is the variable. What is this information, epsilon mu? It's the velocity, but it's also the initial velocity. It just happens to be constant. Okay, and then this information? It's the initial position. Okay. So here I'm explicitly writing down the solution in terms of the initial velocity and the initial position data. Okay. But there you go. I mean, the solution in the most trivial case comes out of this very complicated expression. Presumably it will work in more complicated cases as well. And that is the subject to which we will now turn. Okay? All right. So the next thing I'm going to do is going to put smiles on the faces of many of you, and it is going to cause the rest of you to quiver in fear. That's okay. We're going to make a more general connection between the first and the second definition, and it's going to go by way of something which many of you are very familiar with. So what I'm going to do is, for simplicity, I'm going to work in R2, but I'm going to use something non-trivial. I'm going to use polar coordinates. And in this case, you all know what the line element looks like. It's dr squared plus, and I said polar coordinates, theta and phi. R and theta, how about real polar coordinates in the plane? R squared d theta squared. Okay? The metric, of course, is just 1 r squared. But more importantly, you can construct the Christoffel connection components from this. And the only non-zero ones are these. Gamma r theta theta is minus r. And gamma theta theta r, which of course, because of the torsion-free condition, has to be the same as gamma theta r theta, is 1 over r. Okay? So after the last homework, you are all capable of figuring this out. Obviously, it's not something you need to be able to do in your head, but you've got all these nice formulas you derived for calculating these things for a diagonal metric. This is a diagonal metric, a metric of the space. Looks like that. Okay. So even if you can't do this calculation in your head, the answer is hopefully at least somewhat feasible. So now what I'm going to do is I'm going to consider a path through this space from some point A to some point B. And I'm going to, for now, let the path be arbitrary. And since the coordinates of our space are r and theta, then x mu of lambda really just boils down to r as a function of lambda and theta as a function of lambda. Okay. So x mu has two components, r and theta, and each of those could ostensibly depend on lambda. So this is sort of a setup. Okay? We good? Now, we have to pick how we want to parameterize the path. What are we going to use for our lambda? And I am going to go ahead and assume that lambda is equal to s. That is the length of the path. This is very much like we defined for velocity in special relativity, where we defined the parametrization in terms of proper time, which is also just the length of the actual path through space-time we're moving. So I'm going to choose my parameter s to be that. And so now I'm thinking about my path as r is a function of s and theta is a function of s. Okay. And then we can immediately write down an expression for the total length of an arbitrary path from point A to point B. Okay? So the total length from A to B is the integral from A to B of a bunch of differential lengths. So we take this path and we break it up into a lot of differential segments, and then we go back and add them all together with an integral. Okay? Now, of course, the reason why I do something as stupid as take something finite and break it up into an integral of a bunch of infinitesimal things is because this ds is something which we've already specified for the space. Okay? So, plugging in our expression for ds squared, where of course we have to take a square root. We get something like that. And then what I'm going to do is something that's going to look a little weird. I'm going to go back and reintroduce ds itself. Okay? You can literally sort of see the algebra here. If I take this ds and put it inside the square root, it has to get squared, and then it cancels all the ds squareds in the bottom, and everything goes right back to what I have here. Okay? Sarah, I drew your card.
Okay.
What is the actual value of that thing under the square root?
1.
It's 1, okay? So that's something to keep in mind a little bit later on. All right, now what we're going to do is we're going to take this formula for the length of the path and we're going to extremize it. Okay? We're just going to directly extremize it. How do we do that? Well, if you squint your eyes, this thing right here actually looks a lot like something like this. Okay? Well, what I have in mind here is, maybe I should write it like this, is I have two coordinates, r and theta, and then I can define the velocity of each of these as the derivative of the coordinate with respect to the parameter of the path, which is s. So dr ds is vr, and d theta ds is v theta. And so this guy is just going to become the integral from a to b of the square root of vr squared plus r squared v theta squared ds. And this looks just like a Lagrangian, where instead of thinking about time as the parametrization of everything, we use s. Okay? Well, you guys know how to do this, most of you. If I want to extremize a Lagrangian, where does that lead me? Or sorry. If I want to extremize the integral with respect to time of a Lagrangian, what is this quantity called, by the way?
Action.
That's the action. If I want to extremize the action, where does that eventually lead me? What equations does it eventually lead me to? The Euler-Lagrange equations. Okay? Look, there is no difference between extremizing this and extremizing this. If this leads you to the Euler-Lagrange equations, this is going to lead you to the Euler-Lagrange equations. The only difference is instead of t everywhere, it's going to be s everywhere. Okay? Now for those who don't know, the Euler-Lagrange equations that come from extremizing this look like the following. The derivative with respect to time of the partial of the Lagrangian with respect to one of the velocities minus the partial of the Lagrangian with respect to the associated coordinate is equal to 0. So I get an equation for each and every coordinate, and I form this set of derivatives. Okay? So coming back here, if we want to say that we want to extremize the length, that is, take the functional derivative, the word functional is actually important there, take the functional derivative of this thing and say that it's equal to 0, then this is going to lead me to an analog of the Euler-Lagrange equation. So let's just do that. We're going to have a d by ds of the partial of L with respect to VR minus the partial of L with respect to R. We're going to set that equal to 0, and then d by ds of the partial of L with respect to V theta minus partial L partial theta, and we're going to set that equal to 0. Okay. I don't expect you, I mean, obviously it's nice if you've seen Lagrangian mechanics before you come to this, but you don't have to know Lagrangian mechanics. I'm just giving you these equations. That's all you need to worry about. Okay. Now, our Lagrangian is just the square root of VR squared plus R squared V theta squared. Okay, it's the thing that we're integrating over ds. So I can now actually bang out what these things look like in this example. Okay. Now, when I do this, I'm going to kind of go ahead and streamline the results. There's a lot of overall factors which I'm just going to get rid of, because at the end of the day, the equation's equal to 0. So anything which multiplies the whole equation, you can just divide out. All right? So at the end of this, and after just a little bit of getting rid of things, we find an equation of the following form. D2 R ds squared minus R d theta ds squared is equal to 0, and d2 theta ds squared plus 2 over r dr ds d theta ds equals 0. Okay. And don't worry, I'm going to let you do this in your homework. So you'll get to fill in the details of starting from here with this Lagrangian and generating these specific equations. And one of the key things to remember when you do this, just might want to make a note of this, is that when you're taking the derivative of this thing at various points, you're actually going to have to take the derivative of the Lagrangian with respect to s. But remember that the Lagrangian is really just 1. So it actually doesn't vary with respect to s, so that derivative. So it's effectively a constant. Yeah?
So why did we go through all that rather than just using a geodesic equation?
That's exactly what I'm about to say. Because, yeah, so it's fine. You're projecting what I'm about to say, which is that this set of equations is exactly what we're going to get by taking the geodesic equation with the Christoffel connections and just plugging these into the geodesic equations. So this comes from one method. The other method says, okay, let's write this down. D2, if I use for the first, so when you write this equation down, you will get to pick the value of mu. Mu is the free index here, so you write down the equation once for each value of mu. So if I pick the mu to be, say, 1, so the x1 is the r coordinate, then that equation becomes d2r d, well, my parameter is s, so ds squared, plus, and then I'm going to have gamma r nu alpha dx nu ds dx alpha ds. Okay, this term obviously looks good. d2r ds squared. And now we just have to look here and say, okay, I've got to do a sum over nu and alpha. But I only really need to take into account the terms in the sum that are non-zero. Well, the upper index of the gamma is already r, so the only one that I'm going to get is when the bottom two are theta, theta. So these two have to be theta, theta. That means this is theta, and then I can substitute in minus r. And that's equal to 0, and holy shit. It's exactly what we got here. Okay. And then I'll let you plug in the Christoffel coefficients for the second version of this with respect to theta. So the point of this is I derived this equation from the second definition of geodesics. I said geodesics parallel transport their own tangent vectors. And we stated that in terms of the covariant constants of the tangent vectors, and that led us to this expression. What I just demonstrated for you is that this definition and this mathematical expression is compatible with the first definition, which is I want to extremize the distance between points. You'll end up with the same differential equations. Okay? Other questions? Yeah.
Which came first?
Which came first?
Yeah.
That's actually a really interesting question, because the problem of extremizing things is the extremization of the distance came first. I'm sure, because I think the second definition actually required the advent of. It certainly. You can say the definition, the curve which extremizes the distance, without having invented calculus. To actually calculate it, you need calculus. Okay? But the second definition would never have even come along without calculus. Okay. All right, so I'm going to finish with one more application of this, which will illustrate to you pictorially the situation where you have to maximize the distance, and it's also going to connect to something that you heard from a long, long time ago in special relativity. Yeah?
So you kind of pulled the geodesic equation out of something that was analogous to Lagrangian mechanics. Is there some way to pull kind of two geodesics out of something that's analogous to Hamiltonian mechanics?
I don't know the answer to that off the top of my head, and I'm not going to get into that right now. Let me finish what I got to do, because I'm already done. And then you can come and talk to me after class about that. All right, so and I should say it's not so much Lagrangian mechanics that this is coming from. It's an action principle. That's the key nugget that lets you make the connection. You're extremizing something. Okay, so in a Lorentzian signature spacetime, that is when you have at least one part of the metric, one of the diagonal terms of the metric has minus. So for example, Minkowski space, where the metric in rectangular coordinates is -1, 1, 1, 1, 1, 1, that's Lorentzian signature. Then when we calculate the length of a path, we have to be careful, because in the Lorentzian signature spacetime, ds squared is negative along a path followed by, for example, massive objects. So remember, in special relativity, ds squared looks something like this. We don't have to be in the flat space of special relativity, but that's an example which you're familiar with. One of the things we know that a massive object can do is sit still. That means dx, dy, dz are 0, and it just hangs out and exists in time. So there you go. There's proof that massive objects have ds squareds which are negative, and it turns out you can't change that fact. Okay, if you're massless, your ds squareds are always 0, et cetera, et cetera. Okay, so in order for the square root in our formula to make sense, we have to put a minus in there. And it turns out that in Lorentzian signature with this definition, geodesics actually maximize path length instead of minimizing. Okay? Now that might not be obvious, but let me just give you an illustration to demonstrate to you how this works. So I want to consider, and I'm going to do this in two-dimensional Minkowski space, so all we have is the dt and the dx. So in two-dimensional Minkowski space, where I have coordinates t and a coordinate x, I'm going to start at the point A, and I'm going to go to the point B along two different paths. The first path is just going to be like so. The second path is going to move out to a point here at some constant velocity. I know it's constant velocity because on an x versus t it's a straight line. And then when it gets to this point, it's going to instantaneously turn and come back here. Again, at a constant velocity. Okay? I'll call this path u, and I'll call this path v. And all I want to do is calculate the length of those two paths. Okay? That's all I want to do. Okay, look. Which path is longer?
V.
V?
Oh, wait.
Let's
this is
see.
a trick question. They're the same. No, they're not.
So let me start. let me start with path A. So if I calculate the length of path A, so some SAB, or actually we should call it tau AB. Yes. The length of that path is actually pretty easy because again, this is our definition. But because this doesn't move in x, the ds that we use is just minus c squared dt squared. And when we put the minus in and then plug it in the square root, we're just going to get c dt. And of course, you guys should have just like screamed at me a long time ago. We set c equal to 0 like back in the Stone Age, so there's no c in this story. So this literally becomes the integral of dt.
You said it to 1, not 0, right?
Yes, thank you. That's exactly what I meant. To 0. It's awesome. And what kind of world would that be? Okay? So does everybody understand how I got to this expression? Are we good? You literally just say, I'm only moving in t, so I only have minus dt squared, plug it in there, take the square root. Bam! Hey, Caleb, since you did so good on that previous question, can you do that integral?
Yes.
Yes, you can. Good. What's the answer?
TF minus T0.
Good job. TF minus T0. Sweet. Okay. Now I'm just going to do this along path V. Now along path B, I actually have a change in x, okay, that I have to contend with. And so the integral that I'm doing is going to be the integral of dt squared minus dx squared. Remember, I have to put a minus in there so the signs change on those two terms. But now what I can do is the same trick that I kind of played over here, and that is sort of massage a dt out of this. But now this is an integral over time, so I'm again integrating from t0 to t final. You ready? Caleb? And you can phone a friend if you need to. He might take a while to wake up. When we did this integral, what was the integrand?
1.
It was 1. What can you tell me about this integrand?
It's not 1.
Is it bigger or smaller than 1?
Probably smaller.
It's smaller than 1. So when you do this integral, whatever form this takes, and it actually takes a very simple form here because the vx's are constants. But you could do it more generally. This is going to be less than t final minus t initial, which was the answer I got here. So at the end of the day, as weird as it seems, this path is actually shorter than this path. Now clearly, that means there is no shortest path I can draw, because I can make the path shorter and shorter by just going further and further out. So in this space, the only well-defined extreme is the longest path, and that's this one. Okay? So this does two things for us. One, it tells us why it is that in some cases the geodesics have to be of maximum distance, but it also does something else. Let's put two twins right here. One of them sits at rest. One of them gets in a spaceship and flies away, and then turns around and flies back. When they get back together, which one is older?
One that stood.
The one that sat still, because he existed along a longer path in space-time, and your age is directly associated with the length of your path in space-time. So this resolves the twin paradox for us. Notice it critically hinges on the idea that one of them stops and turns around and changes direction. All right? That's where we're going to end for today. Why was what?
I was at less than 1. Small slope.
Well, this is a positive number, and you're subtracting it from 1. So this is, the inside of this is a number less than 1, and you're taking the square root of it.
I mean, what would stop you from picking like VXs that were decimals so like they were not?
That's fine. So here, square root 1 minus Vx squared. How does that compare to 1? Well, let's square both sides.
Okay, yeah.
And then you have that.
Quick question, this is Dr. Fordham.
Yes.
Is this a 2 or is this